In this video, we will examine the bending of an axially loaded beam that is simply supported at both ends, and specifically we would like to have a look at the point at which this beam will buckle. This video follows on pretty much directly the previous video, which was the analysis of transverse vibrations of an axially loaded beam. A link to that appears above, and if you haven't yet viewed that, you should probably look at that before viewing this video. I remind you that in that video we defined the axial load as being positive in the tensile direction. So the tensile load was defined as positive. Clearly in the case of column buckling, we don't expect a tensile load to be able to buckle a beam. So we would expect the value for buckling to be a negative value, the value of P. So maybe I'm blowing the punchline up front, but just bear that in mind, that when we find the critical load that causes the column to buckle, we would expect it to be a negative value. Let's move this to the side. Now in that video that I mentioned, when we analyzed the axially loaded beam, we came up with an equation for the shape function w of x equals c1 cosh r1x plus c2 sinh r1x plus c3 cosine r2x plus c4 sine r2x, number that 1. And I remind you that r was found from the equation that r1 and 2 squared is equal to p divided by 2ei plus or minus the square root of p divided by 2ei squared plus rho a omega squared divided by ei. And if any of this is a mystery to you, go back and look at that video. So what we need to do in this video is apply the boundary conditions for a simply supported beam. We know what those are. At x equals 0, we know that the displacement w of 0 is equal to 0. And again, I remind you that I'm using capital W's here. The capital W's refer to the shape function, as opposed to small w, which is a function of both x and time. Okay, all the w's for the purpose of this video will be assumed to be capital W's, which means it's the shape function rather than the displacement itself. So applying boundary condition 1 to equation 1 gives us C1 plus C3 is equal to 0, since the other two terms cancel out. We'll call that 3. And then the second boundary condition, at x equals 0, we know that the moment is 0. Therefore, the curvature of the beam is 0. W comma x of 0 is equal to 0. And this yields, differentiating equation 1 twice, minus quantity r1 squared c1 plus r2 squared c3, and that's equal to 0. And it should be fairly clear from these two equations that c1 is equal to c3, and both are equal to 0. Let's number these 4 and 5. And then by substituting equation 5 into equation 1, we can reduce equation 1 to w of x equals c2 sinh r1x plus c4 sine r2x. We'll number that equation 6 and put a box around it. So now we need to substitute the two boundary conditions at x equals L. Let's copy equation 6 to this page. And boundary condition number 3 then would be that w at L is equal to 0. This implies that c2 sinh r1L plus c4 sine r2L is equal to 0. Easy enough, we'll call that number 7. And then the final boundary condition, number 4, w comma xx, the curvature or the moment, w comma xx at L is equal to 0. Taking the second derivative and substituting x equals L into that gives us r1 squared c2 sinh r1L minus r2 squared c4 sine r2L. And that's equal to 0. Call that equation 8. So we're going to write equations 7 and 8 compactly in matrix form. And that is a coefficient matrix times the vector c2, c4 is equal to 0. Call that equation 9. And did I hear someone out there say, but this is the eigenvalue problem? Give yourself 10 points. This is the eigenvalue problem. I hope all of you spotted that. Okay, the eigenvalue problem says that if I've got a matrix of coefficient times two unknowns equal to 0, then for non-trivial solutions, I need the determinant of this coefficient matrix to be 0. Otherwise, I only have trivial solutions, which is C2 and C4 are both 0. So for non-trivial solutions, the determinant of the coefficient matrix must be equal to 0. And the determinant of a 2 by 2 matrix is easy to find. It's just the product of the diagonals minus the product of the off-diagonals. So the product of the diagonals gives us minus R2 squared sinh R1L sine R2L minus R1 squared sinh R1L sine R2L, and that's equal to 0. And since both R1 and R2 are not 0, it means that sinh R1L times sine R2L must be equal to 0. And this, in fact, gives us the transcendental equation for the mode shapes. That sinh R1L times sine R2L is equal to 0. Let's give these some numbers, number 10 and 11. We'll put a box around this intermediate solution. So now we can solve equation 11 for the natural frequencies. Turning the page, we copy equation 11 over. However, we notice when looking at the equation that sinh R1L is always greater than 0 as long as R1L is not equal to 0. So for all R1L not equal to 0, sinh R1L is not equal to 0, it's greater than 0. Call this equation 12. So therefore, if sinh R1L is not 0 for all values of R1L not equal to 0, the conclusion must be that sine R2L must be equal to 0 at all times. And then we've seen this before, where because it's a periodic function, R2L must be equal to integer values of pi, n pi, where n is 0, 1, 2, 3, etc., etc. And the n's, the number corresponds to the mode shape. So we can rewrite this equation as R2 is equal to n pi divided by L. Let's number these, 13 and number 14. And we'll put a box around this intermediate solution. Now we can go back to equation 2, which is the equation for R1 and R2. And since we have this equation for R2, we can substitute equation 14 in. And this gives you that R2 squared is equal to P divided by 2EI. And R2 is the smaller of the two roots, so it's the negative square root. And that's the negative square root of P over 2EI squared plus rho A omega n squared divided by EI. Now I remind you that this gives you an imaginary root. R2 is imaginary because I've got to take the square root of this value, which is necessarily less than 0. So I remind you, if you cast your mind back to your simple harmonic oscillator days where you had something like a root minus k over m, and you decided that that was root k over m times I, what you did is you took out a negative 1, right? We really only cared about the absolute value or the magnitude of what was under there in the case of an imaginary root. So in that same spirit, we're going to take the absolute value of this, and we're going to set that equal to n pi over L quantity squared, and that comes from equation 14. Let's number this 15. And then rewriting this, I'm just going to take out a negative since the absolute value considers the negative and positive case. And I'm just going to flip the order of the terms. The negative is now on the P over 2EI term. And that is equal to n pi over L quantity squared. I think some of you are going to have a few questions about this. Before you ask, just think about it a little bit. Go back to the simple harmonic oscillator and see how we treated it. And convince yourself that we did the same thing. We actually only cared about the magnitude of this, which is why we took the negative. So now we can solve this equation for the natural frequency, omega n. Let's copy that equation over to the next page. And the first thing I'm going to do is take this term and move it over to the right-hand side. Then we're going to square each side. Squaring the left-hand side is dead simple. We just drop the square root sign. And that is equal to the right-hand side all squared. Let's square the right-hand side. It's the first term squared plus 2 times the product of the two terms. The 2 cancels the half, and we're left with P over EI times n pi over L quantity squared, and then finally n pi over L quantity to the 4th power. Now you should notice that this term on the left-hand side cancels this first term on the right-hand side, And now what we're going to do is rewrite this equation in terms of omega. So dividing both sides by rho A over EI gives us omega n squared is equal to EI over rho A times, and I'm just going to switch the order of these two. So that's times n4 pi to the fourth over L to the fourth plus P divided by EI n squared pi squared divided by L squared. And that can be rewritten as EI over rho A, and then I'm going to take out as a common factor n pi over L to the fourth power. And what remains in the parentheses is 1 plus P over EI times L squared over n squared pi squared. Finally, I can solve for omega n by taking the square root of both sides. Clearly, we just need the positive square root since frequencies can only be positive. And that gives us the square root of this is just n pi over L quantities squared, and then the square root of the rest. Square root of EI over rho A times quantity 1 plus PL squared over n squared pi squared EI. And we'll number this equation 16 and put a yellow box around that. That's another intermediate solution. And this is the equation for the natural frequencies of an axial-loaded, simply supported beam. One of the things you hopefully notice here is that the effect of the load P, and I remind you the load is defined as positive when it's in tension, but the effect of increasing P is that it increases the frequency. It has in effect a stiffening effect on the beam. So if a tensile load has a stiffening effect on the beam, we can imagine that a compressive load would have a de-stiffening effect on the beam. So a compressive load, in other words, if P were negative, we would expect the natural frequency to decrease. In fact, if P is negative enough, this term under the square root sign will go to 0 and will make the fundamental frequency go to 0. And as it turns out, that is the definition of the onset of buckling. So what I'm saying is buckling will occur at that load, that compressive load, that causes the fundamental frequency to go to 0. So armed with that knowledge, let's proceed. So first we copy equation 16 down, and then we go ahead and implement for buckling to occur that the fundamental frequency, omega 1, goes to 0. So because we're dealing with a fundamental frequency, n is equal to 1, let's give this a number, 17, and then it should be fairly clear by inspection that in order for omega n to go to 0, this quantity under the square root needs to go to 0. So 1 plus PL squared divided by pi squared EI is equal to 0. And we can solve this for P as P equals minus pi over L squared times EI. The reason for this negative sign is what I indicated earlier, is that it's a compressive load, and only under compression can this column buckle. Let's give it some numbers, 18, 19. And then we're going to go ahead and define the magnitude of this as the critical load. So the critical load, P sub CR, is equal to pi squared divided by L squared times EI. And PCR is the critical or the buckling load. We'll call this number 20, and let's put a box around it. Now, some of you might remember from your strength of materials class that this is exactly the buckling load that we calculated using a strength of materials approach. And you might recall that in order to do that, we actually had to assume some sort of a curvature to the beam. We assumed that the load was a compressive load, we call it P, and that this displacement here we'll call E of x. And we said something like the moment plus P times E is equal to 0. Okay, and from that we were able to put in a mode shape and assume mode shape, and we derived this exact result. So what is the point I'm making here? The point is that the beam did not buckle under strength of materials unless it was deformed initially. In this case, we don't make any assumptions like that. We're simply acknowledging that this is a simply supported beam, and we're observing what happens when the fundamental frequency goes to 0. It doesn't require any displacement at all in order for the column to buckle. It just requires a sufficient axial compressive load so that there's no flexural rigidity, and it behaves more or less like a wet noodle. Okay, and then finally we can substitute equation 20 into equation 16, and we can rewrite equation 16 as omega equals n pi over L squared times root EI over rho A times 1 plus 1 over n squared P over P critical. Call that equation 21, and we put a box around it, we're done. I realize I'm missing my little n here. So in closing, I think there are a few remarks I'd like to make. First of all, it bears repeating that this frequency equation includes the effects of the stiffness of the beam and also the stiffening effects of the axial tensile load. We notice, obviously, that as P goes towards P critical, the frequency goes to 0, but I remind you that P needs to be negative. It needs to be a compressive load. This will never go to 0 as long as P is positive. Additionally, as can clearly be seen from this equation, as P increases, so the frequency omega n increases. And then what is also useful to note is that if P goes to 0, this cancels out and the frequency becomes the frequency of an Euler-Bernoulli beam. We've seen that before. And then finally, if the flexural rigidity of the beam goes to 0, probably easier to see it in this equation up here, then this will tend to the frequency of a string under tension. Well, I think I'm going to cut it at this point. I hope you found something useful in this video. If you have, please go ahead and hit those like buttons so that others can get to see it too. If you have any questions or comments for me or found this video just plain boring, I'd love to hear from you in the comments section below. If you'd like to be notified of new video releases, please click on the subscribe links below and click the bell button. Thank you for watching, and I will catch up with you in the next video.